Okay, good morning, everyone. So we come to lecture 12 today. We're still on group theory. I think this is the fourth group theory. Okay, the fourth one. Okay, in the last lecture, we talked about the characters of the irreducible representations and the orthogonality theorem for the characters. So today we'll just continue on the topic of the character table. So first, the irreducible representation, actually, they provide a good way to define the quantum numbers. So first, let's start with, let's say, the Schrodinger equation. Okay, you have a Hamiltonian first, and then you have a wave function, then you have an energy of the wave function. Okay, so let's say this is usually not just the energy, is usually there is something like IH delta T. Okay, this is a more general form. Okay, so of the Schrodinger equation. So now we define something called a group of Schrodinger equation. So what do you mean the group of Schrodinger equation? That means the symmetry group that commute with the Hamiltonian. So for example, you have a group. The group element is R. Okay, this is the group element. Then you have the representation. You have the representation. I call PR. Okay, PR. Okay, PR is the operator on the wave function. These are operator on the wave function. And they're the representation of the symmetry group. The symmetry group. So if this is the symmetry group of the system, that means, okay, so let me quickly define what you mean by symmetry group. So this operates on the coordinates. And this operate on the wave function. So this symmetry group just operate on the coordinates. For example, rotation, reflection, inversion, they operate on the coordinates. And this one operate on the wave function. So you can define them in this way. If you have a wave function, PR, wave function, let's say F, then you apply this R on the coordinate, and then you apply this operator on the wave function, then they go back to itself. Okay, they go back to itself. That means PR on here equal to F R inverse X. Okay, so that is how you define it. So basically, what this operator does is to cancel the effects of the symmetry operation on the coordinate. And you can easily prove that this PR is a representation of this group. Okay, I think I did something like that in a previous lecture to show that they are indeed the representation. Okay, so the symmetry. So this group, if they commute with the Hamiltonian, for example, if you have a wave function like this, and then You have this way, you have this relationship. Then you apply the PR on both sides. Let me just copy. So let's say you have a wave function like this. Then you apply a PR, a PR on both sides. So because this PR and H, this Hamiltonian, they are the symmetry group of the Hamiltonian. So these two will commute. These two commute. Okay, these two will commute. So basically, if this is the symmetry group, then the Hamiltonian PR will be equal to H. Yeah. So you apply the symmetry operation on the Hamiltonian, you get exactly the same Hamiltonian. Okay. So what it means is that PRH, you apply PR here, you apply PR here, then this is 1. This is 1. So basically it means they commute. That means PR and the Hamiltonian commute. They all mean the same thing. This relationship can go up, you can go down. Okay, like you have one, you have the other. Okay, so basically when you say a symmetry group is the symmetry group of the Schrodinger equation, it basically means you have a group and all these representation elements, they commute with the Hamiltonian. So they don't change the Hamiltonian. On the other way, you can say you let the Hamiltonian go through a symmetry operation, it becomes itself. Okay, they are basically mean the same thing. Okay, here, then you can apply this commutation relationship. Then you also, I mean, E is just a number, okay? Energy, a scalar. So then here you can kind of group it together. So you see that if is an eigenfunction of H with energy En, then PR is also, is also an eigenfunction with energy En. So using the symmetry operator, you can find out the degenerate state. You can find out the degenerate states. And actually almost all the degenerate state can be found out in this way. Okay, it can be found in this way. So there are two kinds of degeneracy. One is the symmetry related degeneracy. And the other is called accidental degeneracy. So what do you mean symmetry related degeneracy? As long as these two degenerate states, they're connected by a symmetry operation, then they are called symmetry related degeneracy. So this kind of symmetry related degeneracy, they're very robust. As long as you have the symmetry, then the degeneracy is always there. And the only way to break the degeneracy is to break the symmetry. Okay, so this is what we're interested in. Anything else is called accidental degeneracy. Like you have a degeneracy, it just happened to be there. They just happen to have the same energy. Okay, and I would say this is relatively rare. Okay, and I would say most of the degeneracy we see in the research, they're symmetry related. Accidental degeneracy is rare. Okay. And sometimes people find something they think it is accidental degeneracy, but later they can find out that there's just some hidden symmetry that you didn't know. Okay. So basically, you should have this kind of a thought, that mindset, that if you observe a certain degeneracy in your experiment, you should immediately consider that there should be a symmetry. For example, if in your experiment you see a certain line, and then somehow you apply the magnetic field or electric field or whatever, you see this line to break into two lines, then immediately you know that there's a symmetry there to cause this degeneracy. You break the degeneracy, you break the symmetry, you break the degeneracy. That should be like a common mindset in your research. Okay, I mean, as you see more and practice more, that will become like your kind of your common sense. Okay. Okay, suppose you apply, you have one, suppose you have a group, you have a group P, PR, and then you have a function, an eigenfunction. Then you apply all of them. You apply all of this symmetry operator on this wave function. Then how many wave functions you get? So let's say you have totally H elements. You have H elements. Then how many wave function will you get? In principle, you will have H wave function here. Okay, you have H wave function here. At most. However, you'll find that sometimes you apply the symmetry operator, you simply got the same wave function, and then times a certain phase factor. Okay, times a certain phase factor. So this H is the at most how many wave function. Okay, so first you know that the number of group elements is the maximum you'll get for the number of degeneracy in your system. Okay, that's the first thing you know. But later you'll find out that if you apply on this, you don't get all H different wave functions. You will get a smaller number, smaller than, I should say, just equal or smaller than H wave function. Okay, so suppose you get two of them. Okay, suppose you get two of them. So eventually you have let's say you apply all of them, you get one wave function, you get two wave function, and then you apply all of these elements, you only get the linear combination of them. Then you'll find that these two elements, this two wave function, they, let's say, yeah. If you find out that PR apply on any one of them, let's say just one, then let me say one, equal to a linear combination, equal to a linear combination. Let me say, let's say the matrix is, let's say the element is this one, and then one, B, one, 2, 2, 1, 2, 1. Okay, and then you have a matrix. Okay, you have a matrix. So basically, these two will form something we call the basis functions. for the representation. Gamma. Gamma, okay? You can say this is gamma 1, whatever you like, okay? So this is the basis function of a representation. So basically, for a Schrodinger equation, you have different eigenfunctions. Those eigenfunctions, some of them will form together to become the basis function for the representation. Okay, so let's do some simple example. Then you have a feeling on what I mean. Okay, so first, let's consider a cyclic group. Let's start from 1D representation first. Let's consider a cyclic group. What do you mean cyclic group? That means you have a group that, let's say A1, you have a group A1, A2, A3, You have a group like this. So they can all be represented as A 3 times, 4 times, and H equal to E. This E means an identity element. Okay, not. Okay, so this is a cyclic group. Then we know that the representation, then you're going to have a representation. Let's say the representation is gamma. Okay, this gamma, the character is gamma because for one-dimensional representation, the trace is the matrix. Okay, the trace is the matrix. So if you do it like this, H times, then let's say the character is R. Okay, let's say the character is R. So from here on, then this A, this number AN equal to gamma AN, because this is a representation, and then equal to Rn. So this will be RH, and then this will be 1. This will be 1 because AH is E, and for the identity representation, it is just 1. It is just 1. So from here, you know the character. I mean, I should not just say character because the character is the whole matrix. It's a 1D. Okay, so from here on, you know it should be R will be a complex number. E 2 pi P over H, and P equal to 1, 2, 3, H. I mean, you can examine this. If you put this number and let it multiply H times, then you have a 2 pi I P. Then you have a E 2 pi I P. Then is 1 P. Then is 1. Okay, so so in this case, each element is one class, because it's a cyclic group. A cyclic group is an abelian group. Okay, so each element here is a class. So when you have each element, so each element means H classes. And then what does it mean? That means H irreducible representations. And here, what are these representations? And this representation is this. And the representation is and the representation is this. So what does it mean? That means if you apply the symmetry operator on the whatever wave function you have in this system, all you get, I mean eigenfunction, of course, then all you do is just to multiply a phase factor there, Okay. So for example, let me give you an example. Let's consider a 1D crystal. A 1D crystal. Let me draw it better. Okay, let me draw it better. Okay, a 1D crystal. And then let's say the lattice constant is A. The lattice constant is A. Okay, so let's say you have a wave function X. Okay, X. Then what is the symmetry group here? What is the symmetry group? The symmetry group is just a translation. Okay, you can translate any number of A, you still get exactly the same thing. I mean, I call dot 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 here. So you have an abelian group. You have an abelian group. If you put the boundary condition to say this atom is exactly the same as this atom, then you make it into a cyclic group. And all you need to do is to make the number more and more. Then you have a larger and larger cyclic group. Then you recover to just a 1D crystal. Okay. Yeah. So this is one application of the example that I show you here for the cyclic group. And here, the representation is just the translation. The translation of a wave function. Let's say you have a wave function here. You do the translation, then the wave function you just move here. You do it again, you just move here. So this is the translational symmetry. Okay. Okay. So this is the translation. So let's say you have a wave function. So all of these are translation. The P, PA. Okay, PA. PA is the represent a translation operation. Over a displacement. Over displacement A. Over displacement A. Basically, what it means is that you have P, A, and then what it does is over displacement negative A. Negative A. So what it does is X plus A. Okay, so this is the definition. The definition. Okay, suppose this is an eigenfunction. Okay, if is an energy eigenfunction. Okay, if this is an energy eigenfunction, then that means PA is also an energy eigenfunction. Because this is a symmetry operator. This is a symmetry operator. So this is also an energy eigenfunction. Okay, then what it means is that this function must be a certain representation A. Actually, they put it must be a certain representation. Okay, because these are all 1D representation. So what it does is this operation is the same as this. So this operator is the same as you just put the matrix here, and this is a 1x1 matrix. Okay. And according to what we have got before, the value will be this value. The value will be this value. Okay, the value will be this value. So we can simply use the index. Simply add the index here to represent it. You said this is a P, this is a P, and then this is the element P, and then this is P. Okay, so eventually, according to what we got here, we will get this factor. Copy. And then, so this is the character, and also the representation for this operator. So the total length. So let's say this is the total length. If the total length is L, then L, then L will equal to AH. You have H element, right? So the total length is L. Then you can replace it. You can replace it. Copy. Then this will be A over H. A over L. A over L. Okay, A over L. Then we define K equal to 2 pi P over L. Then this will be E IKA PX. Okay, so this is the character. This is the character. So we got this result. We got this result. So if you look at this, you find that this is what you learn in solid state physics. Okay, so what function can fulfill this kind of a relationship? The function will have this form. The function fulfilling this relationship has the form of K UK. So this is a periodic function. This is a periodic function. So this is the Bloch theorem. Okay, so the Bloch theorem is basically a certain way to present the representation of a translational group. Okay, so what you see here, this factor is the character of the symmetry group. Okay, so how many character? Then you just count how many classes are there. So the number of classes is just the number of elements. The number of elements is the number of letters. The number of atoms. Okay, so you add more number of atoms, then you just add more classes in your symmetry group. Then you just add more character. Okay, so that's why this is the character. Okay, you add more, you just make the L bigger and bigger and bigger. Then you get more and more. Then the allowed number of P, you see this P, this allowed number of P. If you go to the previous example, this allowed number of P is the same as the number of group elements. Okay, so when you make the lattice bigger and bigger, then you have more and more P. I mean, here, of course, he used the symbol P, means because this corresponds to the momentum. But I mean, you have learned the Bloch theorem before, but here we're trying to represent the Bloch theorem in the language of group theory. Okay, and it's a relatively simple one, a 1D representation. Okay, do you have any questions before we move on? Before we move on. Okay, another example is the two-dimensional rotational group, 2D. So what do you mean 2D rotational group? That means you have a system that is, let's say they are on a cycle. Then you can rotate it. Yeah, for a complete circle, you can rotate it by an angle like this. And the system is exactly the same. The system is exactly the same. Okay, so this is an abelian group. This is an abelian group. Okay, so let's say you rotate. We just let M. We just let M denote the representation. Okay, gamma is a representation. M is the index for the irreducible representation. Okay, so if you rotate for one angle, so you know that according to what we learned before, this is a cyclic group. A cyclic group, the representation is just a set of a complex number. Okay, so you know that it will has a form like this. Okay, it will have a form like this. And because it's a cyclic group, because gamma M 2 pi is 2 pi just the identity element equal to 1. So the M can only be 0, plus minus 1, plus minus 2, plus minus 3. So this cyclic group property, this property require that. I mean, this is a general complex number for any angle. But once you put this condition, then the M can only be like that. Okay, so this M become the indices for the irreducible representation. Okay, so suppose now you really apply. Let's say you have a wave function. Let's say correspond to this irreducible representation. Okay, so we only focus on this angle. Okay, so now you do a rotation on the angle. Let's say you rotate it by this particular angle. Then what does the function change? The function will change into, I mean, all the others are the same. And then this angle will rotate it. Because you actively rotate this, that means you need to go backward, okay, to cancel it. And this, because this is a one-dimensional irreducible representation, you apply on it, the result is only the original wave function multiplied by this, okay, because this is a 1D representation. So all you need to do is copy this thing and then replace this operator by this character, by this matrix, okay? So it's a 1D representation. And then this gamma is just this factor. This gamma is just this factor. Let me see. This is this angle. Because you move this angle. Okay. Let me see. In this case, okay, so then it just goes like this. It depends on your convention. Some people add the minus sign here. Some people not, and it depends on your convention. Okay, it depends on your convention. I think in the textbook, it just give both convention. Okay, it can be this one or the other. It's up to you. Okay, it's up to you because eventually you have the plus and minus sign, so it doesn't matter. I just follow the textbook and then add the minus sign here. Okay, so this is the character. So how do you fulfill this? The wave function that can fulfill this relationship is something like the Bloch's theorem. It's something like the Bloch theorem. The wave function they can fulfill this relationship we have this form. We have a form like this. Okay, and then m equal to plus minus 1 plus minus 2 dot dot dot. Okay, so this is what you get for angular momentum eigenfunction. So this factor, I mean, if you use the language of group theory, what you see this phase factor is just a irreducible representation. So that means those angular momentum wave function with different quantum number, they are the basis functions of different irreducible representations of the rotational group. Okay. You have any questions? Okay, if no, then let's go to the point group. Okay, so there are a lot of point groups we will deal with in solid state physics. So I just maybe I just draw them one by one. Then at least we go through them one by one. Then we know what point group they are. Okay, the first one. There are actually totally 32 point groups. I'm not going to draw all of them. Just draw some common ones. Okay, the first one. Let me just keep copying then. Okay. Okay, the first one is the C1. C1 means no symmetry. No symmetry. So I just follow the textbook to use the cross to represent something on the top or bottom. Okay. So, and then the second one is C2. C2 means you have a cross here, and you have another cross here, and then okay, so you have something like this. So you rotate it 2 times, then you get this. This is called C2. C2 group. Okay, C3. Then you have this, and then you have a triangle. Okay, so this is called C3. Then let me copy. Yeah. Then you have C4. C4 is 1, 2, 3, 4. Yeah. My drawing is not very accurate. Okay, but this okay, this is C4. So there's no C5. No C5. Because C5 is not compatible with the translational symmetry. People see C5 symmetry in something called the quasi-crystal. That means they don't have a long range order. They have probably like some short range order. They can locally have a C5. Okay, but C5 is not compatible with translational symmetry of crystals. And then you have C6. You have C6. I just draw it here then. Okay, C6. C6. C6 is you just draw a hexagon. Something like C6. So this is C6. Okay, now then these are all rotational groups. So now let's add the reflection. Let's add the reflection. So the first one we'll get is is called C2V. So what do you mean V? V means vertical mirror, vertical mirror. What does it mean? So you're going to draw something like this. Draw it like this. Not very symmetric. Let me draw it one more time. You get the idea. Okay, my drawing is not very accurate. Okay, and then you have a plus sign here. Okay. So what do you mean? Okay, first you can rotate it 180 degrees, you get the same thing. But then not only so, you draw a mirror. You draw a mirror here. You also find that this one will go to here. This one will go to here. So there's a vertical mirror symmetry. Okay. And you draw a mirror here. Then this one will go to here. So these are vertical mirror. So this vertical mirror will provide a symmetry. And you don't have this here. So for example, if you draw a line here, you'll find that this cross will go to here, but you have a symbol in the middle that if you do the mirror symmetry, you will get something like this. Okay, so you don't get the same thing. So C2 and C2V are not the same thing. Okay, C2 is you only have the rotational symmetry. You don't have the vertical mirror symmetry. Is it okay? So we'll just go through them one by one. Okay, I mean. Okay, then you go to you go to this C3V. What is C3V? Then you draw it like this. Not very good. You get the idea. Okay, you get the idea. Okay. I don't know how to do it better. Let me try it better. This is slightly better. Okay. Anyway, So then you have a cross, 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 cross. No, you have cross here, and then a cross here. Okay, so how many mirrors are there? They're totally, you can have one mirror, you flip, you have another mirror, you have another mirror, you totally have 3 vertical mirrors together with the rotation. Okay, so this is C3V. And you can continue like that. We can move a bit faster. We can move a bit faster. Let's move up here. Okay, so here you have C4V, C6V. So all you need to do is just keep adding lines. Then here you have four mirrors. You have 4 mirrors. So basically what I'm drawing here is I am adding the mirrors, the vertical mirrors. And then you have this. And you have 4 mirrors. So here you're gonna have 6 of them. Okay, you're gonna have 6 of them. Okay, so this is C6V. Okay, totally 6 mirrors. Okay, now we come to the H one, the CH. What do you mean CH? So I can copy this. C1H. Okay, C1H only have 2 elements, the identity elements, and this horizontal mirror reflection. This horizontal mirror reflection. Now this is H. So this V means vertical mirror reflection. These are the names. So what do you mean? So we're going to use a circle to represent it. Basically, what do you mean? Okay, so let's say I draw a cylinder. So the cross is here, and then the circle is here. Okay, so if you do an operation, if you do a mirror operation, you're going to make this thing go up and this thing go down. The cross and the hole here represent exactly the same thing, but you just move the object from the bottom to the top, to the top to the bottom. So when you look from the top, if your eyes is here, look from the top, so you see something like this, and that means you apply a we use sigma to represent reflection. Okay, so sigma means horizontal mirror reflection. So the sigma operation is to move this hole to the cross and then move the cross to the hole. Okay, so if you only have one element reflection measurement, then this is C1 group, C1H group. Okay, then all you need to do is copy this whole thing. Okay, I'm going to copy this whole thing. Copy to here. Where should I put this thing? Okay, so all you need to do is copy this whole thing here. And then add the circle here. Okay, so everything has a counterpart in the bottom part. Then this is called C2H, C3H, and C4H group. Actually, you also have a C6H. Okay, so do it like that. Okay, so this is the C6H. Okay, so you have two kind of mirrors, vertical mirror and then the horizontal mirror. Okay, now let's come to another one, another type of symmetry group called the S. It's called improper rotation. So this is S2. Is a improper rotation group. So what do you mean improper rotation group? Is that it's like this, you have a hole here, and then you have a cross here. So what do you mean? You need to rotate 180 degrees. Like you rotate C2, and then together with this, and then you get this. Let me actually say it like this. This is the name of the group. This I mean the operator. So what you mean is you rotate 180 degrees and then reflect. Okay, so if you want to draw it like this, it is something like this. So here is this cross is here. Okay, so you rotate and then move up. You rotate and then move up. Reflect. Okay, so then you have a C2. So this is called improper rotation. Just rotation by itself, it doesn't go back to itself. Just reflection, it doesn't go back to itself. You combine both, it works. Okay, so then you have actually three of them. You have three of them. Let me copy. You have three of them. S3, S4, and S6. So it's like this. You have so you have a hole here, two holes, and then two like this. So basically what it means is you rotate 90 degrees and do a reflection, then this point will go back to this. Okay, so this is called S4. Then S6. S6 is like this. You have and then you have this cross. Okay, this is S6. That means you rotate for 60 degrees and you do a reflection, you go back to itself. So this is called S6. Okay. There's no S2, there's no S3. There's no S3. S3 doesn't work. You can try that. S3 doesn't work. If you try S3, if let's say if you try S3, there's no S3. Let's say if you want this, rotate for 120 degree and then you reflect, then you expect something here, right? But then this thing rotate for 120 degree, reflect, then you go back. But then this thing 120 degree go back, then it doesn't go to cross. So there's no S3. You get the idea? Okay. So because S means you rotate for a certain degree and do a mirror reflection, you go back to itself. But S3 odd number doesn't work. Only even number works. Okay, only even number works. Okay, so now let's come to the D. The D group. Okay, the D group is more related to us because both graphene and MOS2 are in the D group. Okay, so let's go to the D group. Let me just copy. Yeah. So the D group goes like this. D2. So what do you mean D2? D2 is like this. You have a line. Actually, people use they use a dashed line to represent it. You have a plus here, and then here. So what do you mean? What do you mean this one? Means when you go from here to here, what you do is a rotation. What you do is a rotation. It's a C2 prime rotation. You have a C2 rotation. So you rotate it 180 degree, you go back to yourself. But here, this is related to rotation. So this one rotate, you go back. So if you want to draw it like that, then basically it's let me see how should I represent it in a more like in a 3D way. So let's say you have a circle. But I'm drawing in 3D. Okay, I'm drawing in 3D. So what it means is that here you have something stick out, and then here, and then here you have something stick out like this, like. And then here you have something stick. Is it understandable? So you rotate it, then this thing will go back to here. Is it understandable? Okay, you rotate it. You rotate it. So this rotate go to here, and this rotate go to here. Okay, not the same as CV. Okay, CV2 is these two are in the same height. They're related by reflection. But this is one is in a higher position, the other is in a lower position. Okay, so after you understand this, the other one is straightforward. Okay, the other one is straightforward. You simply just add the rotation. Okay. Oh, yeah. Okay. You simply just add the rotation. So I just move it quickly then. So we don't have to repeat it again and again. Okay, so this is D3, D4, D6. So this will be something like this. 9. Okay, so basically you just add the cross like this. And then D4 is something similar. Then you add. And then this is D6. D6 has more. Okay, then you, let me make it bigger. Cross. Okay, so these are the D group. They're all rotational groups. Either just rotate. When you add a prime means it's a vertical rotation. When you don't have a prime means it's a horizontal rotation. Okay, now let's come to this D. Let's come to this D2D group. What do you mean D2D? D2D means something like this. And then you have this. Okay, the dashed line means a rotation. The solid line means a reflection. So it's like this. Okay, like this. And then this plus. Okay, so look at this. Let's try to understand it. Okay, so here, this dashed line means you have a C2 prime operation. It go back to itself. But then from here to here, you have a vertical mirror operation. You get the idea? Okay. So here you rotate, you have a C2 prime. And then here, you have a reflection, vertical reflection, you go back to itself. So you have a C2 and also vertical mirror is mixed together. Okay, it's mixed together. So this is called the D2D group. It's not the same as D2. D2 only have a C2 rotation. And it's not the same as now here C2V has this mirror reflection. Mirror reflection. This has a mirror reflection. And then D2 has only the a rotation, but now this D2D has both. So it's a higher symmetry. Okay, so then okay, copy. Then we have this D3D, D3D. D3D. So that will be okay, more and more dense. And then you have dash. Okay, so it will be something like this. Okay, so here you have reflection, and then from here, from this one, you have a C3 prime. So this cross here, you have C3 prime. Prime means it's a vertical rotation. Okay, and this is not sigma V. Okay, so let's go ahead and do the higher symmetry group. The higher symmetry group is H. So this D2H. So D2H is like this. You have a rotation. Yeah. Okay. And then here you have both. You have both. So what do you mean? So first, you have this C2 symmetry. And then you have a rotation C2 prime. And then in the same time, you also have the vertical mirror symmetry. You have all of them. Okay, so this is called D2H group. D2H group. Yeah. Also sigma H, both. So it's a higher symmetry group. Okay, so now let's go to D3H. Okay, D3H. This is the one for MOS2. Okay, this is one for MOS2. So let me see how to draw it. Okay, so it's like this. Okay. I mean, actually, this is the first time that I draw them one by one. I learned it before, but I just simply just look at it. And I actually feel that if you draw that one by one, at least you have I would say a more personal experience with it. This. Okay, so this is the D3H. So this is the one for monolayer. For monolayer MOS2. For MOS2. I think also for graphene. For bilayer graphene. For bilayer graphene is also like that. I think. Let me see. Is it? Probably not for bilayer graphene. I need to double check. But for monolayer MOS2, that is right. Okay, so how many symmetry are there? So you have C3, and then here you have C3 prime, and then you have a vertical, and then you have the mirror symmetry. You can go and check the MOS2. You have the lattice, right? You just check them one by one. You have all of these symmetries in MOS2. Okay, you have all of this symmetry in MOS2. Okay, and then you have a C4H, a D4, D4H. Then this one, I just go faster. Okay. Okay. Okay, so similarly, you have D4. So all the main difference is that it is C3, C4. Okay, the last one is for graphene. This one is for graphene. So this is D6H. This is for graphene. So let me draw it. Okay, so I need to use a finer pen first. So basically, for graphene, you rotate for 60 degrees. You go back to itself. Then you rotate it C2 prime, and then you have a vertical mirror symmetry, and also have the horizontal mirror symmetry. It's a very high symmetry group. Okay, graphene has a high symmetry. Okay, so how many do we get? 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So we're missing 5 of them. Okay. They're not listed. Okay. So there are more. Okay. So okay, so we I just, because the textbook only lists that many, so I just do it like that. Okay. So what time is it now? Okay. So let's continue to deal with something more practical. That is how to understand the character table. So now you know all of this, what they mean. So let's go to the character table. So they're all listed online. They're all listed online. For example, this website, you can easily find a website like that. Let me close them. You can easily find a website like that. You just search for point group character. Then here you have all of this group that I have introduced to you. So if you want to see the character table, all you need to do is to click it. For example, let's say MOS2 is the D3H. So it's this one. Then you click into it. Okay. Close. Okay, then you go to D3H group. Okay, then you see the character table. So these are different classes of the D3H group. Okay, so E identity element is one class. The two rotational operator 120 degree horizontal rotation, that is one class. These two are the vertical rotation. All right, so you go back and look at our plot here. So this is a DH. This is the all the operation. You have this C3, you have this C2 prime, you have vertical one, you have a horizontal one. So you can separate them into, usually one type of operation is one class. If they're the same type, they're the same class. So how many type? You have 1 type, 2 type, 3 type, 4 type, and you also have the S. That means you rotate for, there's one that I didn't write here. You rotate for S3. Like you rotate C3 and do a reflection. You go back to yourself. So this is another type. Of course, identity element is another type. Okay. So how many types? You have 1, 2, 3, 4, 5, 6. You have 6 types of operation. So that's why in the character table you have 6 classes. There are 6 types. Okay. So I show them one by one. So according to what we learned, the number of classes, I mean, I didn't really prove it, but you just take the result. The number of classes are the same as the number of irreducible representation. Okay, so this, you expect 6 irreducible representation. So you see the number here. So you see the letter here. A means 1 dimension. Both A and B means 1-dimensional representation. E means a 2-dimensional representation. So they use a symbol like this. A and B are 1D representation. 1D irreducible. 1D irreducible representation. E is 2D irreducible representation, and then T is 3D irreducible representation. You don't go more than 3D in a crystal, okay, in crystal. So these are the three. When you come here, then you see, what do you mean A and B? So A and B, if you go to this, if you see horizontal, this is 1 and this is -1. So basically they give name because horizontal mirror reflection is a special reflection, and you flip it, you usually either get yourself or negative of yourself. So they want to specify this. So if this is -1, then they just say it is B. If this 1 is A. Okay, is okay? But you have another one called this V. If you do a mirror reflection, you go back to 1. You go back to 1 and -1, then you have A prime and A double prime. They use the prime and double prime to represent the parity of the vertical. So for example here, wait, I think I got it wrong. A vertical one first. Okay. Okay, sorry. The vertical one, the horizontal one, if it is 1, is prime. Okay, sorry. Horizontal one. Then I think what is this B? Let me double check. Oh, sorry. My mistake. My mistake. Okay. This is for the principal operation. If you rotate it a certain angle, you get 1, it is A. If you rotate it a certain angle, you get -1, is called B. Okay, so this one is horizontal. My mistake. Okay, if on the horizontal one you get prime, 1 is prime. If it is -1, you get double prime. Okay, and then there's another one called the I operation, called inversion. Inversion. That means X, Y, Z, they all become negative. If you have 1 and -1 is called U. It's called G and U. It's called G and U. Wait. Yeah, G. G. So G and U. Subscript G and U. So what do they mean? G means is they're Germans. They're Germans. G means I don't know how to pronounce it in German. It's a Geray. Geray means even. I think they're Germans. And then ungeray means uneven. That means odd. Okay. So for example, for MOS2, or whatever, if you see a mole, let's say you see a phonon mole called A1G. So what does it mean? That means this phonon is 1. Okay, if you read the paper, you see a phonon mole is A1G mole. So what does it mean? Means A means it's a 1D irreducible representation. This is means it is non-degenerate. Okay. A1 means A1 is the name of the representation. Means G means G means it is even, parity, under inversion. Okay, so people use the representation to label the different eigenstates. So when you see this label, then you just know the meaning. Let's say there's a E2G. If it is E2G, then the E means is a 2D. Irreducible representation means is a twofold degenerate. And then G means is a even parity. Okay, so that is how you understand the names of those phonon mode. All the eigenmodes, no matter electronic eigenmode, excitons or phonons, as long as they are a certain eigenstate, they all have their own representation. And when you read the representation, then you from the label, you understand what they mean. Is that okay? That is how you communicate to people by using these different symbols. Okay, so let's go and understand. Okay, so let's understand it line by line. If you study MOS2, that is the character table that you use. Okay, A1 prime means it's an identity a representation, so that's why it's all one. Okay, so what has this kind of representation? This is the particular quadratic coordinate. And later we'll deal with it. Okay, so A prime 2, they're all prime because they're all one. So that means as long as you have this class, you expect there's some prime. Okay, so they're all one. However, for this one, if you do a C2 vertical rotation, you expect it will go back, it will become negative. It become negative. So this is a 2D representation. That's why the identity operator is just 1 + 1 is 2. And then these are some of them. That means if you do a rotation like 120 degree, it will become negative of itself. Okay, so and this is double prime. Why it is double prime? Because now the horizontal reflection become negative. Okay, so these are all the characters. For the one dimension, the character is the representation. Okay, because it's 1 by 1 matrix, just one number. Okay, so this is already. So when you see -1, that means if you have a certain wave function belonging to this representation, if you rotate it vertically 180 degrees, that wave function will become negative of itself. That is the meaning of it. The 2D are more complicated to understand because it's a 2 by 2 matrix. The two basis functions will mix together. But the 1D are relatively easy to understand. Okay, the 1D are easy to understand. And then from here, so these are some linear and quadratic coordinates and rotations. I think the X, Y, Z, this basically are vectors. If you see X, Y, Z, that means if you have a vector pointing in the X direction, a vector pointing in the Y direction, a vector pointing in the Z direction, this vector will transform according to this representation. For example, Z, if you have a vector pointing to the Z direction, you do a horizontal reflection, it becomes -Z. That's why it's negative. Okay, but if you also rotate it vertically for 180 degrees, you also get negative. But if you rotate it horizontally for any degree, you get it itself. Okay, this is the same. You rotate and then do a reflection, you get -1. And this is the vertical mirror, you get the same. And these are the 2D representation. That means the XY vector, they will mix together. So they belong to the 2D representation. Okay. So these are just once you know the property of X, Y, Z, then you know their combination property. Okay. So you can deal with them. Okay. So what does this RZ and RXY mean? They are the pseudo vector. They are the rotation. So what do you mean RZ, RX? RX is like this. For example, RZ means let me draw the coordinates. Let me draw the coordinate. X, Y, Z. So RZ means you're going to have a rotation. You're going to have a rotation along the Z direction. Okay, you're going to have a rotation along the Z direction. So let's see how it goes. RZ, okay, you can see the rotation on the Z direction. Okay, you see that if you do rotation for 120 degrees, it is the same. I mean, you can see it, okay? I mean, if you just rotate 180 degrees, that rotation is just the same. However, if you do it vertically 180 degrees, so this whole thing will just flip back. Will just flip back. Like you just use a hand like this, you rotate 180 degrees, you flip back. It becomes -1. Okay. And then for vertical one, like if you make a vertical reflection, it becomes itself. So it's not the same as Z. For Z, you do a horizontally mirror reflection, it becomes negative. But this is a pseudo spin. A pseudo spin means if something is rotating, you do a mirror. Let's say you have a mirror. Okay, you have a mirror. Okay, if something is rotating, you would just see them rotating exactly the same way. Okay, a rotation. Take a mirror image, it becomes itself. If you have a vector, you take a mirror image, it becomes negative. So I should not draw a vector here. It's just a rotation. It's just a rotation. Okay. So a rotation after horizontal mirror symmetry becomes itself. But the vector after mirror reflection, it becomes negative. So we call this is the pseudo vector. And this is a vector. So basically Z, X, Y, Z are the vectors. And Rx, Ry, Rz, they're pseudo vectors. Okay. This is X, Y, Z. They're different. They're different. Okay. So why? Because later you know that for those phonon Raman modes, you have different rotational Raman modes. So for example, you have a molecule. Let's say you have a hydrogen molecule or whatever. Okay, you have a molecule. There are a lot of vibrational modes. Some of them are rotational modes. Some of them are rotational modes. So once you have a rotational mode, they rotate in different axes. Then you just go to this table, you will know that what kind of representation they correspond to. So basically, if you know group theory, you deal with a system with a certain symmetry group. You should, when you study those eigenstates, you should identify each eigenstate with a representation. Every eigenstate has their own representation. You should identify them. Everything in the band structure, everything in the phonon vibrational mode, they have their own representation. So you should know their representation. And the easy way to find it is, if it's a rotational mode, then they belong to one of these two. If it is a vector, later, for example, in rotational group, you have the px, py, pz, then they correspond to these two. If you have a d orbital, then they correspond to these three. They correspond to these three. Okay. So let me give you one more example. Let's say let's go to graphene. Let's go to graphene. Graphene is the D6H. Okay. Okay, you see that graphene has a much bigger table because it has a high symmetry. It has a high symmetry. So how many classes are there? Okay, if you go to our where's graphene? Graphene is here. Okay, so I only draw a few of them, but you can draw a few more. For example, if you move this much, you can have a S6. You move and go up, and then you also have an inversion. Why is inversion? Let's say you go from here to here, like you go across it, you find the corresponding one. There's an inversion symmetry there. Okay, there's an inversion symmetry. Inversion symmetry. And one important thing is that the inversion symmetry commute with all the elements in the group. So it's a special operation. And what else? You have S3. That means you have S6. But if you go like this, if you do a S3, like you move 120 degrees, you go up, you still go back to itself. Okay. So you look at here, you have C6, one type, C3, C2. Just from here, you have C6 and you have C3, and then you have C2. You have C2. Okay. So you have C6, C3, C2, and then vertically you have two kind of vertical rotation. Why? Because you can rotate it here, and you can also rotate it here. Is it? I think so, right? No. I think it should be this one, C2. Because all the other, if you go rotation here, these are just connected by this. You make this, you make this, you get this. Okay, so it is a rotation here that different types. Okay, so there are a lot of operations there. Okay, you can consider them one by one. Okay. Okay, so this is another class. So all of this is one class. Each of them is one class. And then once you have the I, this I commute with every element in this here. So you just put the I on everything here. So whatever you see here, they are just this class with the I. Okay, so like you have this, you put the I there, then they become a S3. You have a C3, you put the I there, you become S6. You have this one, C2 with the I, it's just the same as a reflection. And C2 prime with the I, it just become D reflection. And this one with the I, it just become vertical mirror reflection. Okay? Okay, look at the names. Look at the names. This have A means one dimension. B means is once you have a rotation, they become negative. Okay, actually is the smallest rotation, not C3. If you have the smallest rotation, C6, if this is -1, then it is B. That's why it is called B. Okay, that's why it's called B. Okay, then G means under I, it is 1. They are all even symmetry. And then later you'll find you have the U. Okay, A1U means the parity is -1. The parity is -1. Okay, the parity is -1. And then you have the E2G, means the parity is even. So the I is 2. Once you go down here, you have the E2G, then it's -2. E1G -2. Okay, so 1 and 2 basically means that two different representation. E means the dimension, U and G means the parity under inversion, and A and B means the parity under the rotation. So that is the meaning of all these different symbols. And then you go here, you see how the vectors, if you have a wave function behave like a vector, then that means they will transform according to this representation and this representation. If you're dealing with some Raman tensor, so these are all the tensor elements. So the Raman mode, they will transform according to this way. Okay, they will transform in this way. Okay, so I mean, this maybe in the future I can give you more examples on how to deal with the Raman mode, like which Raman mode is Raman active, which is not Raman active. By checking the character table, you will be able to tell. Okay, so we need more application. So now let me demonstrate you one thing. That is the full rotational group and how it gets split when the symmetry is lower. So in the last lecture, I think after I do this, we're done with the lecture. So in the previous lecture, we have this 4D orbital that is 5-fold degenerate. After you put it in this trigonal prism, they're split into 3 different levels, and they're split in this way. So last time I just used a cartoon to demonstrate to you. Okay, I think I mean, it's a good way to demonstrate why they're split in this way, but you can use group theory to do it more rigorously. I mean, more mathematically, by using the character table. And this can be applied for more complicated situations. So let me tell you how to do it. So first, you need to get the character table for the full rotational group. Okay, so the full rotational group is a extremely high symmetry group. Okay, basically, a full rotational group is a sphere. So how many symmetry operations are there? There are a lot. Okay, so first you have the rotation for a certain angle. Okay, so let me just use an angle then. By angle, and along any axis, along any axis. And then you have reflection. You have reflection. With back to any plane. You can do reflection on any plane, horizontal, vertical, tilted, whatever. You have all of them. Okay. And then you have inversion symmetry. Inversion. Just inversion. And then certainly you have the combination of them. You rotate and reflect. You have all of them. Okay. So basically the highest symmetry you can imagine for like a normal 3D object. It's very high. Okay, it's very high. So there are infinite number of group elements there. So you expect there are infinite number of classes, and you also expect there are infinite number of irreducible representations. Okay, so let's deal with the rotational group first. So each of this, so this is a one class. Yeah. This is one class. Is one class. So rotation of an angle is one class. Is one class. That means what do you mean by one class? That means if you do a rotation, by this angle, and then you rotate this whole thing, like rotate it like this. This rotation can be obtained by this rotation through the let me see. So they can be connected by another rotation, like you first rotate the axis and then rotate along the axis. So these two belong to the same class. Okay. I mean, you can double check it by yourself. Okay. So as long as you know the character for one rotation, you know the character for all of the other rotation. Okay, so now let's get the character for this rotation. Let's get the character. Okay. So for rotation, we know that the eigenfunction, the eigenfunctions are spherical harmonics. We use Y to represent YML. I mean, we already learned this in quantum mechanics. So we now basically state the same thing in the language of group theory. So this is the basis functions. Functions of different irreducible representations of the full rotation group. For example, let me see. For example, air state. If you have an air state, I don't know how to represent the air state. So the air state is a fully symmetric wave function. No matter how you rotate the air state, you get exactly the same thing. So the air state, the air's orbit belong to identity representation. Because air state, I forgot the wave function, but it's a wave function in terms of just the magnitude of the radial, and the spherical harmonic in that case is just a constant. L equal to 0. M equal to 0, L equal to 0. This is a constant. Okay, so S orbital just belong to the identity representation. For the P, you have 3, right? So you have 1 here, and then another one here. I mean, you can use different color to represent their sign. So basically, P orbit to the irreducible representation for the vector. Basically, these are just Z, X, Y. Okay, so they're just the representation for vector. So vector transform just the same way as, so you know that all kind of vector, if you have X, Y, Z, okay, you go through a certain rotation or whatever you like, okay, whatever you like the operation, then it can be represented by a certain representation, okay, by a certain representation. So this matrix, I mean, you know, all the vectors, you apply a transformation on it, rotation, reflection, you can all represent it by a 3x3 matrix, right? So this P orbit, they transform, the wave function transform just the same as the vector. Okay, so you can continue to do this. Okay, so you can represent it like this: P R Y L M. This is the spherical harmonic, and then you can represent it as this. So this L labels the representation. Labels the representation. So there are 2L plus 1 functions. Forming the basis for the irreducible representation. For the irreducible representation, we just use gamma L. So for example, you have, let's say you go to D, you have Y M equal to 2, L equal to 2, okay? 1. 2. Okay, totally 5 of them. So you group this as spherical harmonic for the D orbit. And then you just apply any operation on it. Rotation, reflection, basically what I mean, all operation means any of this. You can apply any of this on it. You'll find that eventually what you got can be represented by a certain matrix. You just copy this. You do a rotation reflection on this set of equations, 5 of them. Eventually, you find that they just become the linear combination of themselves. Okay, then this matrix is the irreducible representation for the D orbit. You can go to the AF all the way. There are infinite number of them. Okay, there are infinite number of them. And all of these are, and actually, if you keep going on, you'll find that you have a representation of the dimension 1. L equal to 0 is 1D. L equal to 1 it will be 3D. L equal to 2, it will be 5D. And then this is an A state, P state, D state orbitals. L equal to 3, then it will be 7D. Then you have the F. So what do you mean? Okay, if you say I want to have something in middle so that it is even 2D, yeah, you can actually do it. You work with the spin. You go to 1/2. Then you have a 2D representation for the spin. Okay, so in order to have all the dimensions, you actually need the orbital and the spin together to form the basis function. Okay, so time is almost up. I haven't go to the most important thing. Okay, let's get the character. Okay, if you apply this on the spherical harmonics along the z-axis, okay, if you do this according to the property of the spherical harmonic, what you will get is you get a phase vector like this. Okay, we deal with this before. Because you're just simply doing a rotation along the z-axis, then this vector will come out. And this is the character. So if you do this whole thing on all of them, okay, so let me copy this. If you do this whole thing on all of them, so let's say you are doing a C rotation. I mean, not just C. Is a P C rotation. It's the representation of that rotation along the Z direction. So what you will get is you have a 2 here, so you negative I 2 L. I mean here is 2 2 alpha. Okay, so this will be 1 alpha. This will be 1. This will be I alpha. This will be I 2 alpha. And all the others are 0. Okay, you get something like that, right? Each of them transform like that. So generally, if you have a L rotated like that, the matrix will look like this. E negative I L alpha, L minus 1 alpha, dot, dot, dot. You have eventually you're all the way dot, dot, dot to the end. You just get I L alpha. All the others are 0. Okay, so you get something like this, but just expand for all the L. So what is the character? What is the character? This is the representation. This is the representation. L equal to 2. And then for this class. So what is the character? The character, you just sum over all of this. You sum over all of this. Okay. So the character for this is you sum them. You sum them together. Dot, dot, dot. It's a geometric series that you can actually calculate it. So you first you extract this thing out. You get this thing out. Then inside you will have k equal to 0 to 2L alpha I alpha k. I mean, I can draw one more step. So this will be 1. This will be I alpha times 2L. Okay. So then this thing is just a geometric series. So you can get the result as 2L minus 1. Okay, I skip this algebra. I think you can do it by yourself. Okay, this geometric series get you this thing. Okay, then you put this thing back into here, and then multiply. So what you need to do is you put this thing back to here, so that you will have this L deleted, and then you have this. Put this, put it here. Okay, you put it back, and then you're going to multiply E I alpha over 2 negative on the top, and then E negative I alpha to the bottom. Okay, if you do this, then you'll get something like this: E I L plus 1/2 minus E negative I L plus 1/2. You just put this here, then you get the number. Then here you have this over 2. Okay, so when you have this minus the complex conjugate, you know it is a sine function. A sine function with a certain like 2i phase factor. And eventually the 2i phase factor will cancel each other, okay, on the top and bottom. So eventually you get this. Okay, so this is the character for the rotation for any angle in the full rotational group. Okay, now let's do the calculation for C3. If you want to get the character for C3, okay, so you just copy. You want the character for C3. So this thing, this these are L, not 1. Okay, these are L. These are L. Okay. Let's focus on the d orbital first. Okay, let's focus on the d orbital because we want to. Okay, let's focus on the d orbital. So L equal to 2. So then, so L will be 2 plus 1/2. This alpha will be what? This means alpha equal to 2 pi over 3. 120 degrees. So 2 pi over 3. 2 pi over 3 over 1/2. I mean, this one is 5 over 2. So it will be 3 pi over 3. So this will be a pi over 3. This will be negative pi over 3. Okay, so you have a negative come out. Then you get -1. Okay, so this is the character for C3. Then let's get the character for C2. Copy. If we do the same thing for C2, so this will be 180 degrees, will be pi. Then you just put pi here. And then this will be sine 5 pi over 2. Pi over 2. So this is just pi over 2. So this will be 1. Okay. So this will be 1. So let's go to this table. Let's maybe go back to MOS2. Where is it? D3H. Okay, D3H. Okay, so let me just copy it first. Okay, let me just okay, let's just copy it. Give me a little bit time. I think it's okay. On this table, there are different elements. You have E, 2C3, 2C. Okay, so I copy some of it. Okay, so these are, so now the 6 of them. Okay, 6 of them. So that means I can put my d orbital here. I can put my d orbit for the d orbit. Okay, for my d orbit. So the d orbit is a 5 times 5 of 5 times 5. Let me. Okay, so let's fill in the character. So this one is 5 because the identity matrix, like 1, 1, 1, 1. Okay, 5. This one we already calculate. This is -1. Okay, because for any 3-fold rotational rotation, you get -1. This one is 180 degree rotation, so we get it. This is 1. So we get it. That is 1. So what about the reflection? Then you have to go back and check the wave function. Okay, here. Okay. Because you can use any basis you like as long as they span this 5 orbital. Okay. So you look at here. If you do a mirror reflection, this one will become 1, right? This one will become -1. This one is -1. This is 1 is 1. This is 1 is 1. So if you write a matrix, like you have a P sigma H, you need to change the basis. You don't use the M. You use this 5 matrix. Use this 5 thing. Okay. I mean, you can still use the M plus 1 or -1. I think it's okay. Okay, 0, M plus 1 plus 1 minus 1, M plus 2, M minus 2. So you're, sorry. Okay, you're gonna get something like this. Copy. Sorry, this is M equal to 0. I mean, this means the state. So for the M equal to 0, 1, for the M equal to 0, 1, you get a character of 1. M equal to plus or minus 1, you get the character of -1. This two, you get a character of 1. Okay. So basically you get 1, and then this one you get a character of -1. This one you get the characters of 1. Okay, you're going to sum over this together. Then eventually your character will be what? Will be 1. So this is 1. Is that okay? If you are not certain, then you just don't use M plus 1 or -1. You just use this 5. You get 1, -1, -1, 1, 1. You just sum them together. Then you get 1. Because all of this, because once you apply the mirror symmetry operation, the matrix will be diagonal. Because all of this just become itself. Okay, maybe I can maybe I can write it this way. Let me write it this way. It would be better actually. So E Y Z E X Z. Okay, so I just use this 5 directly. Okay, that would be easier for you to understand. I think the M one is a bit confusing. So once you apply on this matrix will be 1, -1, -1, 1, 1. All of these all the others are 0. So you sum over them, then the character for this will be 1. Okay, so you get 1 here. This one is just the same because it's still just reflection. For a sphere, it doesn't matter where you reflect. All the reflection are the same, so you always get 1. Okay, you also get 1. Okay, the tricky thing is this thing. This is a rotation plus a reflection, and it turned out that this is also 1. In the morning, I was not able to figure out how to do it, but here I just I mean, because you know this. Okay, what I show you here, this function, you see this z square, yz, xz, xy, this. So basically, it corresponds to this one, and this one. So you expect that the character will be this, and this. You know what I mean? Okay, so if we do exactly the same thing, copy. So then this time you change this into the S3, then what you will expect is you will expect that this thing will give you 1. This thing will give you -1. So this will be 1. Then you have another irreducible representation here, another one here. This will give you, let me see. This will give you -1, the other is 1. -1, this 1. So you sum them together. So the character will be 1 plus 1 minus 1 will be 1. Okay, so you get something like that. Okay, now we're going to apply the orthogonality theorem that we learned before to show the decomposition. So let me quickly copy it. Okay, 1, 1, 1, 1, 1, 1. So I hope you still remember what we learned about the orthogonality theorem before. And it's a simple relationship that helps us to decompose it. 0, 1, negative. Okay, so I think, I copy all of them. So let's going to deal with that one by one. So how do we know how they will so let's follow the formula that we learned before. Okay, so if this sigma d orbit is a certain linear combination, let's say aj of this j, I mean all of this, then this aj, according to the orthogonality theorem we deal with, will be h minus 1 nk. This is the name of the class. Okay, go back and review this formula that we learned before. So this nk is the number of elements in the class. These are the character. And then this is the number of group elements. Okay, let's do it one by one. Okay, copy the first column. Just copy. Okay, so copy the first column. And then copy this column. Yeah. I just write it again then. Okay, 5, -1, 1, 1, 1. Okay, then you can delete all the other. Okay. Okay, then let's do the calculation. So this formula. So here, how many group elements? You have 1, 2, 3. How many of them? Did I write it wrong? Oh, this is 3. I make it wrong. This is 3. Okay, so they're totally 12 group elements. You have 6 here, 6 here. Then you just multiply. You have 5 Then this -1. -1 you need to times 2. Times 2. And then this is 1 times 3. 1 times 3. 1 times 1 is just 1. And then 1 times 2. And then 1 times 3. Okay, so eventually this will be 5 minus 2 plus 3 plus 1 plus 2 plus 3. So this is 3, 6, 7, 9, 12. So you have 1. Okay, so you know this will contain 1. Okay, so you just do it one by one. Let me just make one more example. One more example. Okay. One more example. No. So you just the math are pretty straightforward. I just do a few examples, you immediately know. The orbit. And then this is 5, 1, 1, 1, 1. Okay, so now let's do the same thing. Let's do the same thing. So it's 1/12. So this is I will just make it fast. This will be 5. -1 times 2 will be -2. This sum is -1 and 2, so it's -2. This is 1, 1, so this is 1. This is 1 times 2, so this will be 2. This is -1 times 3, that will be -3. So 5 minus 2 is 3, 1, 2. Okay. Did I miss I? This is 3. This is 3. This is 3. Right. So this is 3. Okay, this becomes 0. This 3 minus 3 is 0. So eventually you get 0. Let me just do one more. Just do one more, because this is the one that we're going to. It will contain this one. Copy. Maybe I just copy the whole thing then. I think that's easier. Okay, if copy the whole thing, I can just use this to erase this. Okay, so then you still do the same thing? Just move it up here. Okay, so here this AJ will be 1/12. This will be what? This will be 10. This will be 10, and then this will be negative. This 1 times 2. This is 3. So this is sorry, this is 0. 0 means 0. Okay. Wait. This is 2. Okay, this is 2. 0, 0. This is 2. This is -1, so it's -2, and then this is 0. So this will be 12. So you get 1. The last one is this. The 0 one I just skipped. Okay. So eventually, let's consider here this. If you consider all of this, So what you will get is this will be 10 plus 2 plus 0. I keep missing this 3 here. Okay. And then this will be -2. This will be 2, and then is 0. So this will be 1. Okay, so eventually you'll find that this d orbit, eventually you will have 1, 2, 3. It will become this plus this plus this. So this reducible representation, it is an irreducible representation for the full symmetry, rotational symmetry group. But once you lower the symmetry to go to D, like this is okay, so you can write it like this. You have 5-fold symmetry. So this is a sigma EL equal to 2 for full rotation group, and this will be D3H. So it will break into 3. Okay, so they will break into 3. It can be A prime, E prime, E double prime. Okay, so that is the main conclusion. You have a full rotational group. The d orbit, they are in this gamma L equal to 2 representation, and this representation is irreducible for the full rotational symmetry group. It's a 5x5 matrices. But once you lower the symmetry to D3H, this representation is no longer irreducible. It becomes reducible. So you can decompose this into the combination of 3 irreducible representation. Okay, so each representation here, they represent a certain kind of degeneracy. Okay, so initially you have 5-fold degeneracy because this representation is 5-dimensional, 5x5 matrices. But after that, it becomes a combination of a 1D representation with 2D representation. So you can actually know the character by looking at here. So this Z2 is in A1 prime. So you know this will be DZ2. And then this E prime is this one. Okay? It has the coordinate transformation, like the representation. So this will be dx squared and dxy. Okay? So then you go back, xz, yz. So this will be xz, xz, yz. Okay, so this is what we got in a previous lecture. So in a previous lecture, I use a graphical way. You see these two have a similar perturbation, so they remain the same. And then the other have a similar perturbation, they should remain the same. Then eventually I reach a conclusion that this two will have the same energy after the perturbation. This have another, this has another. So I just split them. I just use a graphic. I use the graphic. So I think for the first time, okay, from the graphic, you feel it's easier to understand. Okay, but sometimes when the symmetry or some of them are complicated, then it's not that easy to represent by graph. So, and group theory give you exactly the same result, but using purely algebra. You don't need to draw any graph. You just from the character table, like from what you just deal with these numbers, and then eventually you reach this conclusion. And then when you check the character, once you reach this conclusion, you go back and check it. Then you know each orbit what they belong in this new symmetry. Okay. Of course, in this case, is relatively simple. I mean, because we know the d orbit has this kind of property. Actually, once you look at the table, you immediately know, because you know this function, they belong to the d orbital. So you immediately know that d orbital will have one stay here, we have two stay here, another two stay here. So if I ask you what about the p, if you have a p orbit in the atom, now you are put into this you are put into here. Let's say if you don't put the d orbit, you put the p orbit here. The p has threefold rotational, have threefold degeneracy before, right? So, but once you go to this once you go to the D3H group, there's no three-dimensional representation, irreducible representation. You know that the p orbit will also be split. So how will it split? Of course, you can do the same thing as what I did, or do all the algebra. But if you know that the p orbit transform like vectors, you can immediately tell the p orbit will be split into two levels. You have a twofold degenerate level, follow the E prime symmetry, and then you have another one. We follow the A2 double prime symmetry. That you immediately know. Okay, so you can immediately from the character table, you can draw. You can actually already draw it out like this. This equal to 1 will be split into 2. So one will be the E prime, the other will be the A double prime 2. E prime and A double prime 2. Okay. And basically you know that this is the PZ. So this will be the PX, PY, and this will be the PZ. So the atom will have such a splitting. PX and PY, they will have a different energy than PZ. Okay, so this is for the d orbital. This is for the p orbital. You can do something similar when you go to the f orbital, but the f orbital will be more complicated. But I mean, the algebra is follow a similar method. Okay, so I hope you have some understanding now. The algebra in group theory are not that difficult. Just multiplication plus minus. It is really the concept, the understanding that is somewhat difficult. So I hope this example show you how you can use group theory. And when you read the theory paper or experimental paper, people usually use the irreducible representation to denote those states. Then when you see a representation, you have to go back to the character table. Let's say if there's a new material, and then people said, this is a E prime state. Then first, how do you know what it means? First, you need to check the symmetry group of that material. How do you check it? Probably you just use ChatGPT. You type a question. Like actually this morning I tried that. Like let's say you can just ask, what is the symmetry point group of graphene? Then immediately tell you it's a D6H. I mean, only the first line is needed. Okay, and then you can actually can you list the character table for it? Then you see the character table come out. Probably not correct. So is it correct? It looks like it's missing something.
There's more.
There are more. Okay. Yeah. So don't trust it. Okay. Okay. Anyway, GPT is sometimes reliable. Probably in the future they have a more advanced version. Give you a better one, but at least this D6H is correct. Then after you go to D6H, then you just go here, and then you click it, Then you find the corresponding representation. Then from the character, you know the symmetry property of that state. So that is how you communicate. You know the group, and then from the name you know. Yeah, these character tables that they're actually quite useful if you know how to use them. So at the beginning, you don't get used to it, so you feel difficult. But you practice, then you get used to it. It just become like something like the multiplication table you learn in elementary school. Yeah, you just get used to it. Okay, you have any questions?
No, Professor.
Okay, very good. Then I will end the lecture here. Thank you very much.